you have probably never thought about what it would mean to be genuinely motionless. Not motionless in the way that you are motionless when you're lying down, and your breath has gone quiet and the room has gone quiet and everything has slowed to almost nothing. That is stillness of a certain kind, and it is real enough. But actual motionlessness, the state of having no velocity relative to anything at all, is something that does not appear to exist in the universe, not for any piece of matter we have ever located. There is always a frame. There is always something relative to which you are moving, and the number that describes how fast you are moving depends entirely on what you choose as your reference. The Earth spins. You know this. At the latitude where most people who watch channels like this one tend to live, somewhere in the middle latitudes of either hemisphere, far enough from the equator that the curve of the planet is a felt thing in the seasons, the surface of the Earth is moving at roughly 400 to 500 meters per second due to that spin alone, not relative to anything dramatic, just relative to the axis, just the spin. The Earth also orbits the Sun. The orbital speed is approximately 29.5 kilometers per second. Every second, while you are lying there in the quiet, the ground beneath you has moved 29.5 kilometers through space. The direction changes continuously. The orbit is an ellipse, the direction of travel sweeping around like the hand of a clock, never the same twice, always pointing somewhere new. But the speed, the magnitude of it, stays close to that number, 29.5, roughly, give or take the small fluctuations as the Earth moves between its nearest and farthest points from the Sun. The solar system also moves. This is the part that starts to become harder to hold. The entire Sun, and with it, every planet, every moon, every comet, every scattered object in the Oort cloud, every piece of rock and ice and frozen gas at the farthest edges of the solar system's gravitational reach, all of it orbits the center of the Milky Way galaxy. The orbital speed is approximately 220 kilometers per second. The orbit is enormous. At this speed, it takes between 225 and 250 million years to complete a single circuit of the galactic center. The last time our solar system was in the position it currently occupies, the dominant life form on Earth was a synapsid, a creature that was neither quite reptile nor quite mammal, living in a world that had the same sun, the same moon, the same planet, but not a single species in common with this one. 220 kilometers per second, then, in the direction of a point in the constellation Cygnus that we call the solar apex, the point in the sky toward which the Sun is currently heading in its galactic orbit. Not that it will reach it. The orbit curves, the direction shifts, but at this moment the Sun's velocity vector points roughly there, toward Cygnus, toward a point we have given a name because we needed to call it something. And then there is the motion of the Milky Way itself. This is the one that is hardest to place, because when we talk about the motion of the Earth, we have the Sun as a reference. When we talk about the motion of the Sun, we have the galactic center as a reference. But when we talk about the motion of the entire galaxy, the whole disk of it, 300,000 light-years in diameter, somewhere between 100 and 400 billion stars depending on who is counting, what do we use as a reference? The answer, and it is a strange one, is light left over from the beginning of the universe. The cosmic microwave background radiation is not a thing most people carry around in their minds as something they relate to personally, and yet it is intimate in a way that is hard to fully state. It fills space, all of space, everywhere you have ever been, everywhere you have ever looked, in every direction, and at every distance and through every wall and floor and body. There is a faint glow of microwave radiation that is the cooled, stretched remnant of the light that filled the universe when it was young, very young, roughly 380,000 years after the beginning, when matter and radiation uncoupled and the universe became transparent for the first time, and the light that had been trapped in that dense hot plasma was suddenly free to go. That light has been going ever since, for approximately 13.8 billion years, stretched by the expansion of the universe from high-energy photons to the long, cold microwaves they are now, distributed so uniformly across the sky that to a very good approximation, looking in any direction, you see the same temperature, 2.7255 Kelvin, which is about 270 degrees below 0 Celsius, which is the coldest bath you will ever be in, and also a bath you are permanently in, have always been in, and cannot step out of. This radiation is, as close as anything in the universe gets to it, a fixed background, a reference. If everything else is moving and you want to know how fast and in what direction, you measure your motion relative to this background, the way you might measure the speed of a boat by watching the ripples it makes against the surface of still water. And when you do that, when you measure the motion of our galaxy, the whole Milky Way, not just the Sun, relative to the cosmic microwave background, you get a number, 630 kilometers per second. The Milky Way is moving through the cosmic microwave background at approximately 630 kilometers per second, in a direction, in a specific, identifiable, consistent direction that does not change on any timescale we have access to, in the direction of something that for a long time had no name and now has one, a name that is both too large and somehow not large enough for what it points at. Here is the thing about 630 kilometers per second that takes a while to land. It is not a sensation. There is a human reflex, deeply embedded, almost certainly older than language, that says, if something is moving, you should be able to feel it. Motion produces wind. Motion produces vibration. Motion produces the sensation of acceleration at the beginning, the low background drag of momentum at the middle, the lurch of stopping at the end. Every experience of motion you have ever had has come with some sensory signal. The bus starting, the plane banking, the car hitting a pothole, even smooth motion, a calm sea, a slow train, produces some faint proprioceptive signature, some tiny signal from the fluid in your inner ear saying things are moving relative to you. 630 kilometers per second produces none of this. It produces no wind because there is no medium being cut through. Space is not air. The few atoms per cubic meter that exist in interstellar space are so sparse that at any meaningful scale, they simply are not there. You do not feel 630 kilometers per second the same reason you do not feel the 29.5 kilometers per second of the Earth's orbit. There is nothing to push against. There is nothing to tell the fluid in your ears that anything is happening. The body keeps no record of this. The body has no instrument for it. Whatever is happening in your nervous system right now, the faint hum of background metabolic noise, the slow cycling of whatever you last ate working its way through whatever stage of digestion it has reached, the occasional involuntary twitch of a muscle adjusting your weight. None of it registers the fact that you are moving at 630 kilometers per second in a direction you have never been told about, towards something you have never seen, through a universe that is also expanding in all directions simultaneously, and therefore technically making the concept of motion more complicated than this paragraph has so far admitted. The body is a very good instrument. It is just not the right one. What it would take to feel this, if anything could, is not the kind of question that has a satisfying answer. The experience of acceleration is mediated by the inner ear, and specifically by the otolith organs, tiny calcium crystals embedded in a gelatinous membrane inside the utricle and saccule, which detect linear acceleration by the way the crystals lag behind when the head moves. When you're in an elevator that starts moving, the crystals slide. When the elevator reaches a constant speed, the crystals settle. When it stops, they slide again. The system is sensitive to change in velocity, not to velocity itself. Constant motion, no matter how fast, is indistinguishable from stillness, and the motion of the galaxy is, on every timescale available to a human life, constant. The speed does not change perceptibly from second to second or year to year or generation to generation. The direction shifts, but over millions of years, not over anything a nervous system could register. As far as the otolith crystals are concerned, as far as every nerve in your body is concerned, there is no difference between lying perfectly still in a quiet room and being carried through the universe at 630 kilometers per second toward the densest concentration of mass in our cosmic neighborhood. This is not a metaphor. It is just true. The thing that is pulling, the thing we are being pulled toward, is a concentration of mass large enough to redirect the motion of thousands of galaxies simultaneously, and we cannot see it directly, and for a long time we did not know it was there. Not because it was hidden, exactly, but because the Milky Way sits in a position relative to it that made detection difficult in a very specific way. We are not on the near side looking out at it clearly. We are embedded in the plane of our own galaxy, which means that when we look in the direction of the pulling force, we are looking through the thickest part of the galactic disk, through thousands of light years of stars, dust, gas, and emission nebulae, all of which absorb and scatter light at the wavelengths we most naturally look in. The thing was always there. The pull was always happening. But the way we built our telescopes, and the part of the spectrum we first learned to see in, and the particular geometry of our location inside our own galaxy, all of that conspired to make the evidence harder to assemble than it might otherwise have been. It was not invisible. It was just in a difficult direction. There is something slightly specific about that, about being carried steadily and fast towards something that is hard to see because of the way you are positioned relative to everything else. The difficulty is not intrinsic to the thing, it is intrinsic to where you are standing. You are still in your room. The hum of whatever is running in the background of this hour is still there. The stillness you were feeling at the beginning of this is still, in every practical sense, real. Your body is not moving relative to the floor. The floor is not moving relative to the building. The building is sitting on the same piece of ground it was sitting on when the night began, and you are moving at 630 kilometers per second. Both of those things are true. They do not cancel each other. They are not in tension. They coexist the same way that you can be asleep and still alive. The one does not wait for the other to finish. It is that the structure keeps being larger than the previous answer could contain. Every time someone draws the boundary turns out to be inside something bigger. Every time someone names the thing doing the pulling, it turns out to be embedded in something else that is also pulling. The pull does not have a bottom. Or if it does, we have not reached it yet, and the instruments we would need to reach it are the ones we are still figuring out how to build. That is where this goes. That is where we are heading. Right now, tonight, at 630 kilometers per second, and with no sensation of it at all. When the map was wrong in the right way, the measurement had already been made before anyone understood what it meant. That is how these things often go. The data sits in a notebook, or in a column of numbers on a printout, or in the residue of a conference presentation that was mostly about something else, and it waits. Not patiently exactly. Data does not have patience. But it waits the way an unanswered question waits, present and inert, until someone asks the question it is the answer to. In this case, the data was velocity, the velocities of galaxies. By the late 1970s, measuring the velocities of galaxies was not a new thing. Edwin Hubble had done it in the 1920s, not well by modern standards, but with enough precision to see the basic pattern. Most galaxies are moving away from us, and the farther away they are, the faster they are receding. This was the observation that pointed toward an expanding universe. It was also, once the initial shock of it settled into the furniture of cosmology, a fairly tidy result. If the universe is expanding uniformly, then on the largest scales every galaxy should be drifting away from every other galaxy at a rate that depends only on the distance between them. The expansion itself carries them apart, like dots on the surface of a balloon being inflated. The mathematical description of this is the Hubble flow. If a galaxy is at a known distance, you can calculate, from Hubble's constant, how fast it ought to be receding due to cosmic expansion alone, and then you can measure how fast it is actually receding, and the difference, the deviation from the predicted Hubble flow, is called the peculiar velocity. Peculiar in the old sense, specific to that object, not general, not explained by expansion alone. A peculiar velocity is what a galaxy has left over after you subtract out what the universe is doing to everything equally. Peculiar velocities are caused by gravity, local gravity, the gravity of nearby structures pulling a galaxy slightly faster or slower or sideways compared to where pure expansion would put it. In a universe with no structure, perfectly uniform, perfectly smooth, peculiar velocities would be zero for everything. Every galaxy would just ride the expansion. The fact that peculiar velocities exist at all is, in some sense, the signature of structure. The lumps. By the late 1970s, a handful of groups were trying to map peculiar velocities on larger scales than had been attempted before. The method was painstaking. To find a peculiar velocity, you need two things: a distance measurement that is independent of velocity and a velocity measurement that is independent of distance. Getting both for a statistically significant number of galaxies at distances of tens of millions of light years was the kind of project that consumed careers. One of the tools available for this was the Tully-Fisher relation, published in 1977 by R. Brent Tully and J. Richard Fisher. The relation connects the rotational speed of a spiral galaxy, how fast its outer stars orbit its centre, to its intrinsic luminosity. A spiral galaxy that rotates faster is, on average, more luminous. The physics of this has to do with the relationship between a galaxy's mass, its rotation, and the brightness of the stars that mass produces. The relationship is not perfect. There is scatter in it, variation around the trend, but it is tight enough to give useful distance estimates. Measure the rotation speed, look up the predicted luminosity, compare to the apparent brightness, and the distance falls out. What emerged as multiple groups applied this and related methods to larger and larger samples was not what anyone expected. The galaxies were not where they should be, not in terms of their physical positions, but in terms of their velocities. The peculiar velocities were large, larger than the small-scale gravitational effects of individual galaxy clusters could explain. They were not random. Random peculiar velocities would average out over a large enough sample. Some galaxies would be pulled this way, others that way, and the net would approach zero. But these peculiar velocities were not averaging out. They were pointing in a direction. Specifically, they were pointing toward a region of the sky, a broad region, covering something like 1/8 of the entire sky, in the direction of the constellations Centaurus and Hydra, at a distance of roughly 250 million light-years. Something in that direction was pulling, not just the Milky Way, not just the local group, the small cluster of galaxies that includes the Milky Way and Andromeda, and a few dozen smaller satellites. Not just the Virgo cluster, the nearest large cluster of galaxies, whose gravitational influence had already been measured and accounted for. The flow was broader. Hundreds of galaxies spread across an enormous volume of space were all streaming in roughly the same direction, toward the same general region, in a pattern that had to be caused by something very large and very massive sitting in that direction. The group of researchers who assembled the clearest early picture of this included Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner. They became known informally as the Seven Samurai, a name that has the particular quality of being both slightly absurd and completely accurate to the dynamics of the situation. A small group of people doing precise and unglamorous work whose results turned out to matter a great deal. Their 1987 paper presented measurements of peculiar velocities for roughly 400 elliptical galaxies, and derived from those measurements the existence of a large-scale flow towards something they were careful, in that paper, not to over-describe. They called the source of the flow a large mass concentration, which is almost comically understated given what it eventually turned out to imply. But that understatement was deliberate and probably correct. They knew they were measuring the shadow of something, not the thing itself. The thing itself was behind the plane of the Milky Way and could not be directly observed at the wavelengths they were working in. The region where the pulling force was concentrated sits in what astronomers call the zone of avoidance. This is one of those names that is so plain it sounds technical, but is really just accurate. The zone of avoidance is the band of sky corresponding to the plane of the Milky Way, the region where, if you're looking in optical wavelengths, the density of dust and gas in our own galaxy is so high that almost nothing beyond it is visible. Galaxies exist behind it, of course, huge numbers of galaxies. The universe does not know about or care about the plane of the Milky Way, but for most of the history of extragalactic astronomy, the zone of avoidance was more or less a blank on the map, not empty, just unknown. The concentration driving the large-scale flow sat behind it, or near it. A significant fraction of the mass responsible for the streaming motion was located in a part of the sky that optical telescopes could not usefully see. This is why the detection came indirectly, through the pattern of velocities rather than through direct observation of the source. You cannot always see what is pulling you, but if you watch carefully how everything around you is moving, you can infer its existence, its rough mass, its approximate location. Gravity is that reliable. It does not do anything other than what it does. By the early 1990s, the picture had a name, the Great Attractor. The name came from Alan Dressler's popular writing about the result. He was trying to find language that could carry the idea to a general audience, and he reached for something that captured both the scale and the directionality of the phenomenon. Great for the obvious reasons, attractor for the way the mass concentration draws the surrounding matter toward it, or appears to. The name landed, it spread, it entered popular science writing and science journalism, and the vocabulary of people who are interested in cosmology, but do not spend their days doing it. It is still the name most people use. But the name carries assumptions that the physics does not fully support, and those assumptions have consequences for how the thing is understood. That comes later. What matters now is the detection, how it was made, what it felt like from the inside, and what the data was actually saying. Here is what the data was actually saying in the plainest possible terms. When you measure the velocities of galaxies in the local universe within a few 100 million light years, and you subtract out the Hubble expansion, what remains is a pattern. In the direction of the Great Attractor, galaxies are moving faster than the expansion would predict. In the opposite direction, they are moving more slowly. The pattern has a center, more or less, at a distance of around 220 to 250 million light years. The amplitude of the flow, how much faster galaxies are moving than they would be without this pull, corresponds to a mass concentration that the visible matter in that region cannot fully account for. Even accounting for all the galaxies in the direction of the attractor that could be observed, the Centaurus cluster, the Norma cluster, the various other structures in that part of the sky, the mass was not quite right. There was always more pull than the visible mass could explain. Some of this is dark matter, which is expected. The halos of dark matter surrounding and interpenetrating the galaxy clusters were not directly visible, but their gravitational effects were included in the models. Even so, the model strained. Part of the reason for the strain, it later emerged, was that the Great Attractor was not the whole story. It was not the deepest structure, the flow that had been measured, the several 100 kilometer per second streaming of thousands of galaxies toward a region 250 million light years away, was itself part of a larger flow. The attractor was a local maximum in a gravitational landscape that extended much further, toward something much larger, about 550 to 600 million light-years away. This is the Shapley concentration, the densest known concentration of galaxies in the observable universe within several 100 million light-years, And it turns out that the Great Attractor and the Milky Way and the Virgo cluster, and essentially everything in the local universe, is also streaming toward it. The Great Attractor was a real structure, pulling the local universe toward it, but it was also being pulled, along with everything else, toward Shapley. The Seven Samurai had found a real thing. The peculiar velocities were real. The large mass concentration was real, the direction was real, but the edge of what they found was not the edge of the phenomenon. It was just the edge of their instruments. There is something specific about what it means to make a measurement and understand it correctly and still not understand how much of it you are seeing. This is not a failure. It is in many ways the normal condition of science at any given moment. Every correct measurement is a correct measurement of something. The question of how much it is a measurement of, whether the thing you have measured is the whole thing or a part of a larger thing, is a question that the measurement itself cannot fully answer. It requires more measurements, different instruments, different wavelengths, different strategies. The velocity surveys of the 1980s were measuring a flow. They were measuring it correctly. The flow existed. It was pointing toward a concentration of mass. That concentration existed. The scale of the measurement was limited by what they could measure, by the distances at which Tully-Fisher and similar methods gave reliable results, by the sky coverage they could achieve, by the tools they had. Within those limits, the result was correct. But the gravitational source of the flow was larger than what was visible in the direction of the flow. This is a strange situation. You are measuring a river. You can see where it is going. You can measure how fast it is moving. You believe you can see the slope it is running down, but the slope keeps going past where you thought it ended, and the ocean it runs into is further away than the edge of your map. The peculiar velocities implied a mass. The mass implied a structure. The structure, when it was eventually mapped, using infrared surveys that could penetrate the zone of avoidance, using X-ray observations of hot intra-cluster gas, using radio surveys, using all the different instruments and wavelengths that were developed or improved over the following decades, there was not a single object. It was a complex, a web of clusters and filaments and sheets, several of which were already known individually, but whose combined gravitational contribution had not been properly assembled. The Great Attractor region includes the Centaurus cluster at roughly 160 million light-years. It includes the Norma cluster, which sits very close to the geometric center of the attraction zone at roughly 220 million light-years. It includes the Hydra Centaurus supercluster, a broader structure in which both of those clusters are embedded. These are real, massive structures. They do pull. Their combined mass is enough to produce a significant gravitational signature, but to account for the full amplitude of the observed flow, the full 630 kilometers per second of the Milky Way's velocity through the cosmic microwave background, you need to add the Shapley concentration and possibly other structures beyond it that are still being characterized. The Shapley concentration, centered at roughly 550 million light-years, is the densest known region of galaxies in the nearby universe. It contains dozens of rich galaxy clusters, including the Shapley 8 cluster, and its total mass is estimated to be on the order of 10 quadrillion solar masses, that is, 10 million billion times the mass of the Sun. Its gravitational reach extends across hundreds of millions of light years, so the Milky Way and the local group and the local supercluster and everything within several hundred million light years is being pulled primarily by two things: a complex of structures 250 million light years away that we call the Great Attractor, and a much denser concentration 550 million light years away that we call the Shapley concentration, and possibly by other things beyond Shapley that current surveys have not fully resolved. The people who made the original measurements in the 1980s knew they had found something. What they did not know was how much of it they had found. The data was correct. The interpretation was mostly correct. The structure was real. The flow was real. The mass was real. They had a piece of the answer. The piece was big enough to be compelling and small enough to be a beginning. That is in some ways the cleanest possible scientific result. A measurement that is right, that points clearly in a direction, and that contains within it the seeds of a series of larger questions that will take decades to begin answering. Not a triumph, not a dead end, just a direction. The direction in this case is the same direction the Milky Way has always been moving, toward something that keeps turning out to be part of something larger. The edge keeps receding, not because the universe is hiding it, but because the universe is simply very large, and we have been inside it for a very short time, and the instruments we use to see it have a reach that is finite and a history that is short, and every time we extend that reach a little further, there is more to see. The map was wrong in the right way. It was wrong because it was small, but it was pointed in the right direction, and that, in cartography as in cosmology, is where you start. A name that weighs almost nothing, consider the phrase Great Attractor for a moment. Not the thing. The phrase, 2 words, Anglo-Saxon monosyllable plus a Latinate noun with a participial form. Great, as in large, significant, impressive. Attractor, as in something that attracts, that draws other things toward it. It is the name of a phenomenon. It is also, and this matters, a very specific kind of name. It is a name given by someone who needed to describe something to people who were not specialists. It is a name chosen for reach, not precision. It arrived not in a scientific paper but in popularizations, in the language of explanation rather than measurement, and it carried with it the weight that all explanatory names carry, the implication that the name describes the thing. It does not describe the thing. This is not a criticism of the name. It is just true. Attractor implies a center, a point, or a tight region that draws things in. It implies that if you drew the gravitational field lines, the curves along which matter naturally accelerates, they would converge. They would terminate somewhere. There would be a place. The Great Attractor does not work like this. What the name points at is not a single object. It is not a dense point mass. It is not even a well-defined cluster of mass with clear edges. It is a region, a broad zone of enhanced mass density, spanning something like several 100 million light years, containing dozens of galaxy clusters, thousands of individual galaxies, and vast quantities of dark matter distributed in ways that are not uniform, not symmetric, and not, on the whole, especially attractor-like in the intuitive sense of that word. The Norma cluster, which sits near the geometric centre of the Great Attractor region, was long considered the most likely candidate for the core of the attractor. It is a rich, massive cluster. It is probably the most massive individual structure in that part of the sky. But mass modelling of the peculiar velocity flows suggests that the Norma cluster alone is not massive enough to account for what has been observed. The pulling is more distributed than a cluster. There is also the matter of what is behind the great attractor, the Shapley concentration, which, as described earlier, may contribute more to the Milky Way's peculiar velocity than the great attractor proper, sits far beyond it. So the Milky Way is being pulled toward the great attractor, but the great attractor is itself being pulled toward Shapley. The attractor is in motion toward its own attractor. This is not a contradiction. It is just how gravity works at large scales. Everything pulls everything else. The structures that look like attractors from one vantage point are themselves being attracted from another vantage point. There is no anchor in this system. There is no place that is purely pulling and not also being pulled. The name Great Attractor was first used extensively in Alan Dressler's 1987 book aimed at general audiences, and in the popular articles that accompanied the Seven Samurai's scientific results. Dressler was trying to communicate something genuinely difficult, that there exists in a certain direction a gravitational influence so large that it is moving our entire galaxy at hundreds of kilometers per second, and that we cannot see the source of this influence directly because of the way our own galaxy blocks the view. This is a real challenge. You want to convey scale. You want to convey directionality. You want to convey the strangeness of being pulled towards something invisible. Great Attractor does all of these things in 2 words. It is efficient. It lodges in the mind. But once it lodges, it does something to the picture. It makes the phenomenon feel more discrete than it is. It suggests a there, a somewhere you could point to, a place the Milky Way is heading toward. It implies arrival is at least conceptually possible, that there is a destination. Here is what the gravitational landscape in that direction actually looks like, as best as current surveys can describe it, and I am not sure I fully understand the geometry of it myself, which may be part of the point. Imagine standing in a shallow bowl. The bowl is not perfectly circular. It is somewhat irregular, lumpy, with a few places where the curvature is steeper and a few where it is flatter. You are near one edge. The centre of the bowl, the lowest point, the place your marble would naturally roll toward if you put one down on the surface you're standing on, is at a distance from you that is hard to estimate because the bowl is enormous and you cannot see the whole shape from where you're standing. Now expand the bowl so that the centre is 250 million light-years away from you. Fill the bowl with galaxies and dark matter and hot gas and clusters and filaments. Make the bowl 3-dimensional, because space is 3-dimensional. And now realize that the bowl itself is not stationary. It sits on a larger slope, tilted towards something 500 million light-years further along, and that larger slope may itself be tilted towards something we have not yet characterized. You are not rolling toward the center of a bowl. You are rolling along a gravitational gradient that is itself not flat, a surface with curvature at multiple scales, each nested inside a larger curvature, each with its own direction and magnitude, and all of them adding up to the net velocity that the instruments measure as 630 kilometers per second in a direction we have named. The direction is real. The name is a simplification. Both of those things are fine. Science names things, and the names are useful, and the names are not the things. This is not unusual. What happens, though, when a name becomes the primary way an idea is held in the public mind? What happens is that the name starts doing work that it was not built to do. Great Attractor implies a specific thing in a specific place. It implies a drama, a vast gravitational engine drawing the universe toward it. It implies that we are falling, that there is a direction we are falling in, that the falling will eventually end somewhere definite. None of these implications are exactly wrong, but none of them are exactly right either. The actual picture is quieter and stranger. It is not falling toward a point. It is flowing along a slope. The slope is real. The flow is real. But there is no point. There is no drain at the bottom of the tub. There is just contour, the shape of the mass distribution in the local universe, and the response of everything in that universe to that shape. And the shape is not fixed. It changes as the universe evolves. Galaxies continue to merge and cluster. The voids between them continue to grow. The filaments of the cosmic web shift their positions over billions of years as gravity slowly draws matter together. The gravitational landscape that exists right now, that is producing the observed peculiar velocity of the Milky Way right now, is a snapshot of a structure that has been building for billions of years and will continue to evolve for billions more. The thing the name points at is a moment in the life of a structure. There is something worth sitting with here, not a scientific point, more of a textural observation. The names we give to things in science, especially to large, complex, not yet fully understood things, carry an authority they have not quite earned. They feel like arrivals when they are really just markers. The Great Attractor is a marker placed in the data by people who were trying to communicate clearly and responsibly about something they had measured but not fully explained. The marker worked. It oriented people toward the phenomenon. It made the phenomenon discussable, but the marker is not the phenomenon. The phenomenon is a distribution of mass across hundreds of millions of light years, structured in ways we are still characterizing, exerting a gravitational influence we can measure but only partially explain, pulling our galaxy in a direction that is also the direction our galaxy is pushing the structures behind it, in a chain of pulls and pushes that extends to scales we have not fully surveyed. The name Great Attractor makes this feel like it has an answer. It has some answers, but the answers it has are nested inside larger questions, and those questions are nested inside still larger ones, and the naming has a tendency to make that nesting feel more resolved than it is. This is not a problem unique to cosmology. Every field names its half-understood things, and the aims help, and the names also stick around after the understanding has outgrown them, and then the names start to become a kind of friction. Great Attractor is useful. It is also slightly in the way of the actual picture. Both can be true. What 600 kilometers per second feels like start with a nerve? Any nerve. The ones in your fingertips that register pressure are good for this. They are the ones you use most consciously, the ones closest to the surface, the ones that return the clearest signal of what is happening at the boundary between your body and the world. A signal travelling along a sensory nerve fibre, a myelinated A-beta fibre, the kind that handles light touch, moves at somewhere between 30 and 70 meters per second. This is fast by biological standards. Fast enough that you do not perceive a delay between touching something and knowing you touched it. The signal reaches the spinal cord in tens of milliseconds, is processed, routed to the cortex, integrated, and delivered to whatever part of your awareness is paying attention to your hands. 70 meters per second. At the absolute fastest end of sensory nerve conduction. 630 kilometers per second, the speed of the Milky Way through the cosmic microwave background, is 9 million times faster than that. 9 million times the speed of the fastest signal your nervous system can produce. Not 9 million% faster. 9 million times. This ratio is the first way into understanding what the number means, or rather into understanding why the number cannot be felt. It is not that the number is fast and our nerves are slow. It is that the ratio between them is so extreme that the comparison barely makes sense. You're not moving slightly faster than your nervous system can register. You're moving in a category that your nervous system has no instruments for, has never had instruments for, evolved in conditions where this speed was never once a relevant variable, never influenced survival, never needed to be measured, never produced a consequence that required detection. Your nervous system is very good at what it is built for, but numbers that cannot be felt can sometimes be heard. There is a version of scale that the ear handles better than the mind. Duration is one of them. The ear passes rhythm, the spacing between events, the pattern of silences, the timing of returns, more automatically than the eye passes spatial proportion. A number that seems abstract when written becomes more physical when you hear it in sequence. So, consider a pulse, 1 beat per second. The tempo of a resting human heartbeat is somewhere between 60 and 100 beats per minute, which means 1 beat per second is on the slow side of resting. The pace your heart goes when you're in a room like this, at this hour, doing nothing more demanding than listening. Now, if each beat represents 1 kilometer per second of velocity, how many beats until you reach 630 kilometers per second? 10 seconds to reach 10, a minute to reach 60, 10.5 minutes to reach 630, 10.5 minutes of 1 beat per second, 1 kilometer per second counted out in single pulses to cross the distance between the speed of 0 and the speed at which our galaxy moves through the background radiation. That number is not especially large, actually, when stated that way. 10.5 minutes is not an overwhelming duration. You have spent 10.5 minutes doing things far less worth your time. But the pulse framing does something useful. It gives the speed a shape in time. It makes it traversable, at least in the imagination. And traversable is an interesting thing for this speed to be, because in another sense it is not traversable at all. Here is a companion number. At 630 kilometers per second, starting from where the Earth is now, how long would it take to cross the distance to the nearest star? Proxima Centauri, roughly 4 1/3 light years away. About 2,000 years. At the speed at which our entire galaxy is moving, the speed that feels like stillness in our bones, you would need 2 millennia to reach the nearest other sun. 2,000 years of non-stop travel at 630 kilometers per second. The speed is real. The speed is fast by every standard available to human experience, and the speed is nowhere near enough to cross the gulf between here and there on any timescale that could be called a journey. The universe has a specific texture at this scale. It is not a texture of objects separated by distances. It is a texture of distances so large that the objects are almost footnotes to the space between them. The stars are not the point. The space is the point. The matter is a residue, a foam, a thin scattering of mass over volumes so large that if you could look at them from outside, if you could somehow see the entire local universe as a single object, what you would see would look almost entirely empty. And in that almost entirely empty space, everything is moving. All of it, constantly, in directions determined by the gravitational field generated by whatever clumps of mass happen to exist nearby, and further away, and still further. The movement is not chaos. The movement has structure. The peculiar velocities are correlated. Nearby galaxies tend to move in similar directions, because they are responding to the same gravitational sources. The flow is coherent. It has a pattern. The pattern is toward the region we have been calling the Great Attractor. But the pattern is also toward Shapley, and the pattern is also slightly away from the great voids, the empty regions, because those empty regions, having less mass than the surrounding filaments and clusters, push matter outward rather than drawing it in. Motion in the universe at large scales is the sum of all of this, pulling from the dense regions, pushing from the voids. The net velocity is the vector sum of 1,000 influences, each real and physical, each adding its contribution to the direction and speed at which any given piece of matter is currently travelling, 630 kilometers per second in the direction of the Centaurus Norma region, is the net, the sum, the result of everything acting on the Milky Way at once. There is a specific quality to that number, 630 kilometers per second, that has nothing to do with its magnitude and everything to do with its precision. It is not a round number. It is not 600 or 650 or 700. It is 630, give or take, with uncertainties that have narrowed over the decades as the measurements have improved. The lack of roundness is meaningful. It is the signature of a measurement, not a calculation. Nobody computed this number from first principles. Nobody predicted it. It was measured, extracted from the pattern of temperature anisotrophies in the cosmic microwave background, from the tiny asymmetry that our motion introduces into what would otherwise be a perfectly uniform glow. When we move through the CMB, the radiation in the direction we are heading is slightly hotter. The photons are slightly blue-shifted, arriving at slightly higher energies because we are moving toward them. In the direction we are moving away from, the radiation is slightly cooler. The photons are slightly red-shifted. The temperature difference is tiny, about 3 millikelvin, 0.003 of a degree. But it is real, and it has a direction, and from that direction and that temperature difference the velocity can be extracted. 3 millikelvin of temperature asymmetry, translated through the physics of the Doppler effect, produces 630 kilometers per second in the direction of a specific point in the sky. The number is the shadow of a physical fact. The fact is motion. The motion is real. The question that is slightly hard to settle, and I think this is genuinely unresolved in a way that is worth being honest about, is whether 630 kilometers per second is fast in any meaningful cosmic sense. In one frame, it is extremely fast, faster than any human-made object has ever moved. fast enough to reach the moon in less than 10 minutes, fast enough to travel the diameter of the Earth in about 20 seconds. By any standard applicable to human experience, this is a very large velocity. In another frame, it is modest. The escape velocity from a galaxy cluster, the speed required to escape the gravitational well of a large cluster, is in the same order of magnitude. The internal velocity dispersions of galaxies within clusters often reach several hundred kilometers per second. So the Milky Way's bulk motion is, in the context of galaxy cluster dynamics, not especially unusual in magnitude, though its coherence across hundreds of millions of light-years of space is notable. In a third frame, the frame of the universe as a whole, the frame of the Hubble flow, 630 kilometers per second is very small. The recessional velocity of a galaxy at 1 billion light-years, due to the expansion of the universe alone, is already several tens of thousands of kilometers per second. At current cosmological parameters, the Hubble constant is around 67 to 74 kilometers per second per megaparsec, meaning that for every megaparsec, about 3.26 million light-years of distance, a galaxy recedes about 70 kilometers per second faster. The peculiar velocity of 630 kilometers per second corresponds to a Hubble flow distance of roughly 10 megaparsecs, 32 million light-years. On cosmic scales, the peculiar motion of the Milky Way is a local perturbation, a ripple. The number is fast, the number is modest, the number is a ripple. All of these are true depending on the frame. What 630 kilometers per second actually feels like, in the end, is exactly the same as what 0 kilometers per second feels like. The room you are in, the particular weight of this hour, the breath that does not quite finish before the next one starts. The number does not land in the body. It never does. It lands somewhere else. Somewhere that is not quite the mind and not quite the senses, some middle place where a fact can exist without being fully absorbed, where a measurement can sit and be accepted and still not quite be believed. You are moving at 630 kilometers per second. The room is quiet. Both of these things are happening simultaneously in the same universe, involving the same matter, and neither one cancels the other. That middle place, the place where both are true and neither is felt, is where this science lives. The structure's behind the structure. There is a moment in any map-making process, and this is true whether the map is of a continent or a neighborhood or a brain or a galaxy cluster, where the person doing the mapping runs into the edge of their instruments, not the edge of the territory. They have been drawing carefully, filling in what they can see, marking what is certain and leaving blank what is not, and then they arrive at a place where the data runs out and the blank space begins, and the blank space is not empty. It is just unknown. The blank spaces on the maps of the local universe, as they existed in the late 1980s and early 1990s, were significant. They were not uniformly distributed. They clustered in specific directions. The zone of avoidance, where the plane of the Milky Way obscured the background. The edges of the velocity surveys, where the Tully-Fisher calibrations became unreliable. The far side of the Great Attractor region, where the signal-to-noise was lowest. In those blank spaces it was already suspected that something significant was sitting. This chapter starts at that threshold, not at the discovery itself, but at the moment just before, when the measurements were good enough to know that the model was missing something, but not yet good enough to say what. At the scale of the Great Attractor, roughly 250 million light-years, the universe is organized into a structure called a supercluster. Superclusters are the largest gravitationally bound or quasi-bound structures in the universe. They are not exactly what the name implies. A supercluster is not a very large cluster in the way a large city is a very large town. A supercluster is an extended region of enhanced density that may contain dozens of individual galaxy clusters, hundreds of groups, and vast sheets and filaments of galaxies spread across tens to hundreds of millions of light-years. The Great Attractor sits at the heart of the Hydra Centaurus supercluster, which is part of the Laniakea supercluster, the structure that the Milky Way is a small member of. But Hydra Centaurus was known before Laniakea was defined. The structure was visible. The density enhancement was real. The problem was that its boundaries were uncertain, its mass was uncertain, and the relationship between the local velocity field and the structure of the mass distribution was complicated by the zone of avoidance sitting squarely in the direction of the concentration. To understand what is actually there, in that direction, you need to see through the plane of the Milky Way. And to see through the plane of the Milky Way, you cannot use optical light. The dust in the galactic plane absorbs and scatters optical light with great efficiency. A star that sits on the far side of the galactic centre, 30,000 light-years away from us in the plane of the galaxy, is essentially invisible at optical wavelengths because of the integrated column of dust along the line of sight. Galaxies that lie behind the galactic plane, at distances of tens to hundreds of millions of light-years, are even harder to see. They are smaller, fainter, and the optical path length through the dust is the full thickness of the galactic disk. But other wavelengths penetrate the dust. Near-infrared light, wavelengths just longer than the red end of the visible spectrum, is much less affected by dust extinction. X-ray photons, which are extremely energetic, pass through the galactic plane with relatively little attenuation. Radio waves are largely unaffected. Beginning in the late 1980s and accelerating through the 1990s and 2000s, surveys at these wavelengths began to reveal the structure of the zone of avoidance in detail that optical surveys simply could not achieve. The near-infrared surveys, including the 2-micron all-sky survey, the IRAS Galaxy surveys, and eventually the 2MASS redshift survey, began to show the distribution of galaxies behind the dust plane. Clusters and filaments became visible that had previously been blank on the optical maps. The Norma cluster, already known from radio and X-ray observations to be a massive structure in the Great Attractor region, appeared in its proper context. Not an isolated cluster, but a node in a larger filamentary structure, connected to other clusters by chains of galaxies that the dust had been hiding. X-ray observations contributed something different: the hot intracluster gas. Galaxy clusters are filled with diffuse gas heated to tens of millions of degrees by the gravitational collapse of the cluster. This gas emits X-rays, and X-rays can be detected even through the galactic plane. The Rosat satellite, operating from 1990 to 1999, conducted an all-sky survey in X-rays that revealed cluster after cluster in the zone of avoidance, including several previously unknown clusters in the Great Attractor region that contributed additional mass to the already complicated picture. Zoom out one step. At the scale of the Great Attractor, 2 to 300 million light-years, the dominant structure is the extended mass concentration we have been discussing, but around it, and connecting it to its neighbours, are the great filaments of the cosmic web. The cosmic web is not a metaphor. It is the observed large-scale structure of the universe, derived from surveys of millions of galaxies, verified by cosmological simulations, and explained by the physics of structure formation from small initial density fluctuations amplified by gravity over billions of years. On scales of hundreds of millions to billions of light-years, the universe is organized into a foam-like network, long filaments of galaxies and dark matter forming the edges and faces, clusters sitting at the nodes where filaments intersect, and vast empty regions, voids, occupying most of the volume. The Great Attractor region sits at the intersection of several of these filaments. The Centaurus wall and the Norma wall, large-scale sheets of galaxies, converge near the centre of the Attractor region. The clusters that make up the densest parts of the Attractor are embedded in these walls and filaments, drawing material from the surrounding volume along the filaments toward them. The peculiar velocities of galaxies in this part of the universe trace this structure. Galaxies on the filaments are moving toward the nodes, galaxies in the walls are moving toward the clusters, and everything together is moving, at the larger scale, in the direction of the Shapley concentration. Zoom out one more step. The Shapley concentration, at roughly 550 million light-years, is the densest known region of the observable universe within that distance. It was first catalogued by Harlow Shapley in 1930. He noted a concentration of faint nebulae. At that time, the extragalactic nature of most nebulae was still being established, in the direction of the constellation Centaurus. It was not recognized as a dynamically significant structure until much later, when spectroscopic surveys revealed that it was not just a concentration of galaxies in projection, but a true three-dimensional overdensity at a consistent distance. The Shapley concentration contains at least 30 rich galaxy clusters, with the central region dominated by the clusters Abell 3571, Abell 3558, and Abell 3556, among others. The total mass of the Shapley concentration is estimated at somewhere between 1 and 10 times 10 to the 16th solar masses, depending on how the boundaries are drawn and what assumptions are made about dark matter content. Even at the lower end of this estimate, it is an enormous concentration. Its gravitational influence extends across hundreds of millions of light-years. The question of how much Shapley contributes to the peculiar velocity of the Milky Way versus how much comes from the Great Attractor region has been debated and revised as the measurements have improved. A 2000 study by Paolo Ficcardi, Bruno Moreno, and Giancarlo Vettolani estimated the Shapley contribution at roughly 25% of the total. Later studies, with better data, pushed the estimate higher, some putting it at 40 to 50%, others at over half. The uncertainty reflects both the difficulty of the measurement and the genuine physical complexity of the situation. The two attractors are not independent. The Great Attractor region is itself being pulled towards Shapley. The separation between contribution from the Great Attractor and contribution from Shapley is not clean because the mass distribution is not cleanly separated. Zoom out one more step. Beyond Shapley, the structure continues. The Perseus-Pisces supercluster at roughly 250 million light-years in a completely different direction, roughly opposite to the Great Attractor in the sky, is itself a large concentration, though smaller than Shapley. The Coma supercluster at 330 million light-years is another significant structure. This Sloan Great Wall, identified in 2003 from the Sloan Digital Sky Survey, is a vast filamentary structure roughly 1 billion light-years long, roughly 1 billion light-years from Earth, containing several superclusters. At these scales, the peculiar velocity of the Milky Way is a local perturbation, influenced primarily by the structures within several 100 million light-years, with the contribution from more distant structures diminishing as the inverse square of the distance. The universe is not pulling the Milky Way primarily toward the Sloan Great Wall. It is pulling the Milky Way primarily toward the dense structures in its immediate cosmological neighborhood, with the Great Attractor and the Shapley concentration as the dominant terms. But even that statement contains an assumption that the dominant contributions are from known structures. Whether there are significant mass concentrations further away, beyond the current survey boundaries, contributing importantly to the observed peculiar velocity, is not definitively settled. There are some indications from the observed pattern of the velocity field that the standard model, with the Great Attractor and Shapley as the two main attractors, may not account for everything. Certain aspects of the observed flow field show residuals, departures from the model prediction that might indicate additional structure, additional mass, additional pull from directions and distances not yet well characterized. The map is good, it is not complete. There is a specific quality to the picture that has emerged from all of this, from the infrared surveys and X-ray catalogues and velocity field analyses and numerical simulations, that is worth pausing on. It is not the quality of a mystery solved. It is the quality of a structure understood in outline but not in detail, characterized in its major features but not in its minor ones, explained in its general behavior but not in every specific deviation from that behavior. This is not a criticism of the science. The science is genuinely impressive. The fact that we can map the large-scale structure of the universe out to several 100 million light-years with any reliability at all, that we can extract peculiar velocities from galaxy redshifts, model the gravitational field implied by those velocities, compare the model to independent mass surveys, and identify the dominant sources of the local peculiar flow, is not a trivial achievement. It required decades of survey work, multiple generations of instruments, and the accumulation of data from millions of individual observations. The picture that has come out of all of this is, in broad outline, coherent. There is a large mass concentration in the direction of Centaurus Norma at 200 to 250 million light-years. There is a much larger and denser mass concentration at 550 million light-years in roughly the same direction. Both are pulling the Milky Way. The combined effect accounts for most of the observed peculiar velocity. The structures are embedded in a cosmic web whose large-scale geometry has been mapped out to several billion light-years by galaxy surveys. The picture is not complete. It probably will not be complete in our lifetimes. The blank spaces are smaller than they were in 1987, and they will continue to shrink as surveys improve. But they are still there, and in some of them, there may be things that will require the picture to be revised again. The structures behind the structure go on. Each time you think you have found the frame is inside a larger one. What the void is actually doing. There is a place roughly 300 million light-years from here where almost nothing exists. Not almost nothing in the way that deep space is almost nothing. That almost nothing still contains gas and dust, and the occasional photon doing its long business. This is something quieter. This is a supervoid, a region of space roughly 300 million light-years in diameter, where the average density of matter is perhaps 30% below the cosmic average. 30% below does not sound like much until you consider what the cosmic average means. The cosmic average density is already essentially nothing by any human standard, about 5 hydrogen atoms per cubic meter, spread across all of space. 30% below that is about 3.5 hydrogen atoms per cubic meter. In practical terms, both numbers describe an absence so complete that the difference between them can only be measured statistically by counting galaxies in a volume and comparing to what the average predicts. And yet the difference matters enormously, because where there is less mass, the gravitational field is weaker, and where the gravitational field is weaker than average, matter is not drawn in, it is expelled. This is not obvious at first. Gravity, in the most intuitive framing, pulls things toward mass. More mass means more pull. Empty space should just be neutral, not pulling, not pushing, just there. But in a universe where the cosmic average density is a real quantity, where every region is, in some sense, measured against what the typical region contains, a void is not just neutral, it is below average. And being below average in a universe where the average is the background against which all dynamics play out, means that matter at the edge of a void is being pulled less toward the void's interior than toward the denser regions outside it. The result, viewed from outside, looks like the void is pushing. It is not, strictly speaking, pushing. Gravity does not push. But the absence of pulling, in a universe where everything is pulling to some degree, is functionally equivalent to a push. Matter at the edge of a supervoid is subject to gravitational forces that point preferentially away from the void's center toward the denser structures surrounding it. The void's interior is a gravitational low, and the surrounding matter flows away from it along the gradient toward the surrounding filaments and clusters. Supervoids, then, are contributors to the large-scale peculiar velocity field just as surely as the dense structures are. They push matter away from themselves, adding to the velocity of galaxies that are already being pulled toward the dense attractors. The flow toward the great attractor and Shapley is not caused only by the gravity of those structures. It is also driven by the voids on the opposite side. Vast emptiness behind the Milky Way, pushing it forward along the gradient. One of the largest known voids in the local universe is the KBC void, identified by Keenan, Barger and Cowie in 2013. It is centered roughly on the Milky Way itself and extends to a radius of about 1 billion light-years. We are inside it. The local group, the Virgo cluster, the Laniakea supercluster, all embedded in a region of space that is substantially underdense relative to the cosmic mean. the existence of the KBC void, and whether it is large enough and deep enough to influence the observed peculiar velocity of the Milky Way, is debated. Some analyses suggest it can explain a portion of the Hubble tension, the discrepancy between different measurements of the Hubble constant, by biasing local measurements of the expansion rate relative to the global average. Other analyses contest this. The KBC void is real. Its dynamical significance is uncertain. What is not uncertain is the general principle. Voids push. Dense regions pull. The observed motion of the Milky Way is the sum of these two kinds of influence, the pull from Shapley and the great attractor on the front side, and the push from the voids, including potentially the KBC void, on the back side. The direction of travel is the same whether you call it being pulled or being pushed, but the mechanism is different, and the distinction matters for understanding the structure, because it means the dynamics of the local universe are shaped not only by where the mass is, but by where it isn't. There is a simulation, part of the Constrained Local Universe Simulations project, based on the observed peculiar velocity field, that tries to reconstruct the density and velocity field of the local universe from the available data. In these simulations, the large-scale structure comes alive in a way that static maps do not convey. The filaments flow, the voids expand, the clusters grow. The Milky Way traces its path through the simulated universe, moving along the gradient from under-dense regions toward dense ones, carried by the sum of all the gravitational influences that the simulation has been constrained to reproduce. Watching the simulation, and this is something that the images of it do not fully capture, only the animations, you get the sense of something organic. Not in a loose metaphorical sense, but in the precise sense that the structure is doing what structure does when you let it run. It forms, it flows, it concentrates. The voids clear out as matter drains toward the filaments. The filaments thicken as they collect more matter. The clusters at the intersections grow denser and denser over billions of simulated years. And through all of this, the Milky Way, represented by a single point in the simulation, or a single small region, moves steadily along the gradient, toward the attractor regions, away from the void. This is not a metaphor for anything, it is what is happening. The void behind us is emptying very slowly as the matter in it flows toward the surrounding structure. We are part of that flow. We have always been part of that flow. The emptiness is not passive. It is active in its own way. Not because it contains some force, but because in the economy of gravity, the absence of mass is as consequential as its presence. You are being pushed by nothing towards something. Both the nothing and the something are real. We will never arrive. At some point, and the physics makes this point reachable, at least in principle, the question becomes, what would it mean to arrive? Not whether we will arrive. That is a separate question, with a cleaner answer. The question of what arrival would mean is harder. It requires thinking about what the great attractor, or the Shapley concentration, or the larger gravitational basin that both of them inhabit, actually is. It requires asking what the endpoint of the motion would be if the motion had one. And when you ask that carefully, the answer starts to slide. Orbiting this question reveals something important. If the Milky Way is moving toward a concentration of mass, the naive expectation is that it will eventually get there. This is how gravity works with a massive body, and a smaller body in the simplified case. The smaller body falls toward the larger one, accelerates as it approaches, reaches a closest point, and, unless it has enough velocity to escape, falls back, oscillates, eventually merges. Gravity makes things come together. The direction of motion is toward more mass. The endpoint is contact. But the naive case requires the target to be stationary, and the great attractor is not stationary. The Norma cluster and the surrounding mass concentration are themselves moving. Moving toward the Shapley concentration, which is moving toward other structures, which are moving in response to their own gravitational environment. The target is not a fixed point. It is a moving thing in a moving universe. The Milky Way is not chasing something that is waiting for it. It is chasing something that is also, in its own way, chasing something else. This is not unusual in gravitation. It is precisely the situation of the Earth and the Moon. The Moon is falling toward the Earth and has been falling toward the Earth for 4.5 billion years and has not hit it yet because the sideways velocity of the Moon is just right to keep the fall curving around the Earth rather than into it. Orbits are falling that keeps missing. In the case of the Moon and Earth, the geometry is clean, a closed ellipse, stable on human timescales. In the case of the Milky Way and the Great Attractor, the geometry is not clean. The mass distribution is not a point. The trajectory is not an ellipse. The universe is expanding, which adds a complicating term to all of this. The expansion of the universe is the thing that prevents arrival in any simple sense. Dark energy, the term we give to whatever is causing the observed accelerating expansion of the universe, is not a pulling force. It does not attract matter. It does the opposite. It drives space itself apart, adding a term to the effective force on any two objects that grows with distance. At small enough distances, within gravitationally bound structures like galaxy clusters, the gravitational pull between objects is strong enough to hold them together despite this expansion. The Virgo cluster, the Norma cluster, the Shapley concentration. These are structures where gravity is one. The individual galaxies within them are bound to each other. The expansion of the universe cannot pull them apart. But between structures, in the vast spaces between clusters and superclusters, the dark energy wins. The space between clusters is expanding. It has been expanding for billions of years and will continue to expand. Faster and faster as dark energy comes to dominate more and more over the diluting effects of matter. Structures that are not gravitationally bound to each other are being carried apart by the expansion, regardless of any peculiar velocity they have toward each other. The question of whether the Milky Way is gravitationally bound to the Great Attractor, whether the mutual gravity between the Milky Way and the mass concentration in the Centaurus-Norma region is strong enough to eventually bring them together, despite the expanding space between them, depends on whether the two structures are already gravitationally bound. The analysis is complicated, and I do not think anyone has given a definitive answer that I could cite with full confidence. But the current understanding is that the Milky Way, the local group, and the broader Virgo supercluster may be loosely bound within the Laniakea basin, while the full Laniakea structure is probably not a gravitationally bound system in the long run. Laniakea was defined as a basin, a region of space whose matter flows converge toward a common centre. But a basin is not the same as a bound structure. The water flowing down a hill converges at the bottom of the basin, but if the hill is also moving, if the whole landscape is being pulled apart, the water may never reach the bottom. The basin defines the flow, not the destination. And then there is the matter of the great attractor itself. The Norma cluster and the surrounding concentration will not wait indefinitely. Over cosmic time, the structure of the universe evolves. Clusters grow by accreting material from their surroundings. Superclusters, over long enough timescales, either collapse into giant structures or get pulled apart by dark energy. The predictions depend sensitively on the total mass of the structure and the strength of dark energy, both of which have uncertainties. What cosmological simulations generally show is that the future of the local universe, over timescales of tens to hundreds of billions of years, involves the gradual collapse of the gravitationally bound components, the local group eventually merging with the Virgo cluster and a few other nearby groups into a larger bound structure, while the unbound parts, most of Laniakea, everything beyond it, recede into the dark, carried away by expansion until they cross the cosmic horizon and are lost to observation permanently. In this picture, the Milky Way does not arrive at the great attractor in any conventional sense. It moves toward the center of the Laniakea basin for a while. Billions of years, maybe tens of billions of years, before the expansion of the universe, the evolution of the cluster, and the redistribution of mass within the bound regions all combine to produce a future that looks nothing like arrival. More like a long, slow reorganization of the local bound matter into whatever configuration gravity and dark energy and time together produce. Arrival, as a concept, requires a destination that stays put long enough to be reached. The universe does not offer that, at least not at these scales. At the scale of a planet and its moon, the destination is stable on human timescales. At the scale of two galaxies, the Milky Way and Andromeda are approaching each other and will collide in roughly 4 to 5 billion years. Arrival means something. A merger, a violent disruption of both galaxies' structures, the eventual production of an elliptical galaxy from what are now two spirals. That arrival is real. The trajectory is calculated. The collision will happen. At the scale of the Milky Way and the great attractor, the situation is different in kind, not just in scale. The great attractor is not a stable destination. It is a node in a structure that is itself evolving. The peculiar velocity of the Milky Way toward it will persist for a long time. But what the Milky Way is heading toward will not look the same when the Milky Way is much closer to it than it does now. The target is a moving, evolving, distributed structure in an expanding universe, and the concept of arrival, reaching the center, stopping, being there, does not map onto it cleanly. This is not a failure of physics. Physics does not require arrival to make sense of motion. Motion is a state. It has direction and magnitude. The direction and magnitude are meaningful and measurable. The fact that there is no clean destination does not make the motion less real. What it means for the motion to be permanent, ongoing without a clear end state, for as long as the observable universe continues to evolve, is something I find difficult to state confidently, not because the physics is unclear, but because the concept itself is strange. We are accustomed to motion that has an end point. Things fall and stop. Things travel and arrive. Things orbit and return. The motion of the Milky Way toward the Great Attractor does not belong to any of these categories. It is more like the motion of a river toward the sea, except that the sea is also moving, and the river is partly being carried by a wind that is also partly carrying the sea, and the whole system is operating on timescales so long that the river and the sea and the wind will all have changed their characters completely before anything resembling resolution occurs. The motion is real. There is no arrival. Both of those things are stable features of the situation, and between them, in the space where arrival would go if it were possible, there is just the ongoing fact of movement, the 630 kilometers per second, the direction toward the Centaurus Norma region, the tug that has been operating since the Milky Way formed and will continue operating for longer than anything we can meaningfully imagine. The question of what it means dissolves when you hold it long enough. What remains is just the motion, the quietest discovery. In 2014, a paper was published in the journal Nature with the title The Laniakea Supercluster of Galaxies. It was not a discovery in the traditional sense. Nothing was found that had not been seen before. No new object appeared in the data. No previously unknown structure was identified. The galaxies that make up Laniakea had been catalogued. Their velocities had been measured. The broad shape of the local velocity field had been characterized. What the paper did was draw a line. The authors, R. Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomered, used a catalogue of galaxy peculiar velocities derived from the Cosmic Flows project to reconstruct the three-dimensional velocity field of the local universe. The method, called Wiener filtering, takes the observed velocities and smooths them into a continuous field, allowing the calculation at any point in space of which way the local matter is flowing. From that field you can identify basins of attraction. A basin of attraction, in this context, is a region of space where all the matter is flowing toward a common center. Draw the boundary around that region, the surface where the flow changes from inward to outward, and you have defined a supercluster. The boundary they drew enclosed a volume of roughly 100 cubic megaparsecs. It contained roughly 100,000 galaxies. Its total mass was estimated at roughly 10 to the 17 solar masses. The center of the basin, the point toward which all the flows converged, was in the direction of the Great Attractor, near the Norma cluster. They named it Laniakea. In Hawaiian, Lani means heaven, Akea means spacious, immeasurable. The Milky Way sits near one edge of it. What makes this a quiet discovery rather than a dramatic one is that the line drawn was a choice, not a finding. The velocity field does not contain a natural boundary in the way that the surface of a planet contains a natural boundary. The flows change gradually. The point where inflow transitions to outflow is not a sharp edge in the data. It is a continuous transition, and where you draw the line depends on how you smooth the data, what resolution you work at, what threshold you use to define predominantly inward flow. Different analyses using different methods and different data sets give somewhat different definitions of Laniakea. Some analyses define it more narrowly, some more broadly. The 2014 Tully et al. Result has been influential. It is the definition that appears in most subsequent discussions, but it is not the only possible definition, and subsequent work has refined and in some cases questioned it. This is the part that I think gets lost in the way the discovery was communicated. When Nature published it, and when their press release went out, and when the videos and the explainers appeared, the framing was almost universally, "We have discovered our cosmic home. We have mapped the supercluster we live in. We now know where we are." The tone was of arrival, of a long search concluded, a boundary finally identified, a home finally named. But what was actually done was more modest and in some ways more interesting than that. What was done was the application of a consistent physical definition, a basin of attraction, to a data set that had been assembled over decades, using a method that makes explicit the choices embedded in the analysis and the resulting picture. The result is a picture. The picture is useful. The picture is not the truth. It is a representation of the truth, generated by a specific set of choices that will be refined and revised as the data improves. The deeper question, the one that the quiet version of this discovery raises, is what it means to belong to a structure. The Milky Way flows toward the center of Laniakea. This is a fact about the current velocity of the Milky Way. It is a present tense fact. The flow exists now. The direction is now. But Laniakea as a basin is not permanent. It is a snapshot of the velocity field at this moment in the universe's evolution. As the universe expands, as dark energy continues to drive the distant parts of Laniakea away from the center, the basin will change shape. Some regions currently inside Laniakea will transition to flowing outward. The boundary will shrink. On long enough timescales, the basin that the Milky Way belongs to will be a smaller one, just the local group eventually, as most of the surrounding structure gets pulled away by the expansion of the universe. The name Laniakea will still apply to the structure as it was defined at this moment in cosmic history, but the flows that defined it will have changed. Membership is not eternal. It is conditional on the current state of the velocity field. What I keep coming back to with this discovery is the act of defining the boundary itself, not the boundary's content, the act. To say, here is where our neighbourhood ends. To draw a line around a region of space and give it a name is to do something that has no counterpart in pre-modern human experience. No previous generation of people knew there was a neighbourhood at all. They knew there was a sky. They knew there were patterns in the sky. The idea that the sky has a structure, that the lights in it are organized into a hierarchy of clusters, superclusters, basins of attraction, each nested inside a larger one, is a development of the last 100 years. The idea that we are inside a particular level of that hierarchy, and that we can name the level we are inside, is even newer. Thule and his colleagues did not discover that we belong to Laniakea. They constructed a definition under which what we already knew becomes organized into a shape. The shape is real. It reflects real velocities, real mass distributions, real flows. But the name, and the boundary, and the sense of belonging, those are added by the humans doing the constructing. This is not a criticism. This is what cartography is. Maps are not nature. Maps are the result of people deciding which features of nature to represent, at what resolution, with what conventions. The map of Laniakea is an excellent map. It is the most accurate map of our cosmic home that has ever been made. And it is still a map, a representation, shaped by the choices of the people who made it, carrying their decisions about what to include, where to draw the line, and what to call what they found. The quietest thing about this discovery is that it was a discovery at all. It was in some ways a formalization, the application of a rigorous definition to something that had been suspected for decades. The structure was always there. The flows were always happening. The belonging was always real. The naming made it possible to point at it. That is not nothing. Pointing at things matters, but it is quieter than arriving. The sensation, again. The room is the same room. You're in it. The hour is the same hour or close enough. The low hum of whatever runs at night is still there, underneath the particular quality of quiet that this hour produces. Your body is where it was when this began, horizontal or close to it. Eyes probably half closed by now, the signal chain between the outside world and the parts of you that process it running at reduced speed, handling only what comes through. This is the state in which information settles differently, not better, not worse, just differently. The resistance is lower, the automatic questioning is slower. Things that would get examined and cross-referenced and held up for scrutiny in this daytime can, at this hour, simply be received. So receive this. You are made of matter. The matter was made in stars. The stars condensed from gas that was shaped by the large-scale structure of the universe. The same structure that is right now, pulling you at 630 kilometers per second through the residual light of the beginning of everything. The Great Attractor is not a story about something out there. It is a story about what matter does when you leave it alone for 14 billion years. It clusters, it flows, it organizes itself into sheets and filaments and voids, and then it flows along those structures toward the concentrations, and everything moves, all at once, in a direction. You are moving in that direction, right now, without sensation, without effort, without ceasing. The science in this narration is not metaphor. None of it was. The 630 kilometers per second is a measured velocity. The Great Attractor is a real concentration of mass. Laniakea is a real basin. The Shapley concentration is a real structure. The voids that push, and the filaments that guide, and the dark matter that shapes without being seen. All real, all present, all operating on the matter you're made of at this moment. The absence of sensation is not the absence of fact. It is just the limit of the body. The body did not evolve for this scale, it evolved for other things, for the grain of the ground and the distance between eyes and horizon and the timing of days, for speeds of meters per second, not kilometers, for distances of kilometers, not megaparsecs, for structures that last a lifetime, not structures that last billions of years. The brain can hold these larger scales. It can learn the numbers, follow the logic, feel something approaching understanding when the picture assembles itself. But it cannot feel them in the sense of sensation. The gap between knowledge and sensation at this scale is permanent. What has been described in these chapters is, in a sense, a portrait of that gap. The gap between the motion and the stillness, between the 630 and the quiet, between the structure that pulls and the body that cannot register being pulled. The gap is not a failure, it is a feature. It is what allows you to be a coherent organism at the scale of organisms, to have a body that works, that maintains itself, that responds to the world it evolved in, while being simultaneously embedded in a structure so large that the body has no instrument for it. You can know the structure, you cannot feel it. Both of those things are permanent features of being a living thing in this universe. The data still has residuals. The structure is larger than what we have mapped. The pulling goes on, in a direction that keeps revealing itself to be the direction of something even larger, even further, even less completely characterized. This does not make the science incomplete in a way that should disturb. It makes it incomplete in the way that all good science is incomplete. It has reached the edge of what the current instruments can see, and beyond that edge there is more, and the instruments are improving. What is already known is enough to change the quality of the stillness you are lying in. The room is not a fixed point. The stillness is not stillness. The night you are in is the same night, and a different one, now that the 630 has been sitting in it.